Can you see my screen, please? The slides. Can somebody unmute and check the slides?
Yes, sir. Yes, sir. Yes.
Hello, can you check the slides?
Yes, sir. We are getting
visible.
Oh, okay, good. So let us start. Okay, we are all set. So today, as I promised that we will dive much deeper into how the images and diffraction patterns are formed, and how to control the electron beam to form diffraction pattern, bright field, dark field, center dark field. Actually, this we are going to understand why do we need center dark field, and we'll also learn STEM, okay, scanning transmission electron microscopy. And after that, we learn convergent beam electron diffraction, CBED, and then tilt and scanning, because if we have convergent beam, then we need to do the scanning. And finally, we'll learn holocon electron diffraction. So in principle, in electron microscope, there are two systems. One is illumination system and second is image system. So illumination system is the system, lens systems and aperture systems, which is above the sample, right? So you have an electron source, and then you have a couple of condenser lenses, C1, C2. Then you have this condenser and objective lens pair, and then you have then the electron beam, whether it is parallel or convergent, that passes through the sample. So this system is basically illumination system. You illuminate the sample, right, using all these optics above the sample. And after that, once the electrons exit from the sample, then you have to form the image, whether image is diffraction pattern or anything else. So that control is image system. So let us see. So there are two ways. Let us first understand the illumination system. And today, actually, you are going to learn a lot more about lenses. You already know how the lenses are formed and what are the aberrations, spherical aberration and chromatic aberration. Last time we learned. So it is not. There is nothing new today, as I always say about my lectures. I'm going to just take you deeper into the same thing. You can see the content. I have already taught diffraction pattern, bright field, dark field, and all kinds of things. So what is new? I mean, let's see. So the students who could not understand, who were not there in the earlier session, so they will also find it very useful. So there are two ways in electron microscopy that you can eliminate the basically sample. You can see this floodlight flooding the stadium. So basically the stadium is your sample, and these are basically electron rays. So basically they are flooding all your sample, right? Equally, there's so you can imagine that this is basically a parallel beam. So you select a larger area, and you have a selected. You want to investigate the entire area, the chemistry and physics of entire area. So even biology. So you flood the entire area, you select it, right? The beams have to be parallel to each other. So, right. And the second case will be that you select a small area. So you have like a spotlight. So this is not the case in electron microscopy. Basically this cone is inverted. So just for analogy, I try to find this image. So basically you select the smaller area, right? This is basically convergent beam. So it will be right inverse of this. So the advantage is that here the disadvantage is that you are looking at the larger area and the sampling size is much bigger. So you get the information, for example, from a very large area. Here you can select what you want. For example, a player on the field, then you can investigate. So for this purpose, you have to scan the beam because, for example, this beam is placed in the stadium. So you have to keep on, like you can see on the stage, right? The beam keeps on moving. So how can we do that in electron microscope? So many students requested last time at NCL, in my NCL class, that why didn't you teach that? When we want to understand what is going on. So normally I don't teach this this particular basically class, this one, but because there was some requests, so I, from the last previous batch of chemistry students, so that I thought let me include that. And it basically gives advantages to all the students, because it takes you a little bit deeper. There is no new thing which you are going to learn, right? So it doesn't overload you with a lot of information. It just takes you deeper into the same information, right? So you're not getting overloaded. So I make sure that you are not like completely overwhelmed with a lot of information. You can see that all these things we have learned in past, nothing is new. It's like a revision for us. So you can see this is basically electron source. This is lab 6 crystal, single crystal. So the electron starts emitting from here, this pink one, the pointed one, and then immediately there is a Venel cap. This is negatively biased. So this is very important part, Venel cap. So this is to focus the basically diverging electron. So this negative field focuses this electron beam to a pointed spot. Actually, you want a point source. So this is called gun crossover. This is considered as a source. Actually, the source length is calculated from this point, not from this point. I have been telling you. After that, you have an anode plate. For example, you say that your microscope is working at 200 kilo electron volt. So that voltage is applied here. You can see this positive sign here, and you can see this negative sign here. And you can change this voltage. You can see this is a sign where you can change it, and this is ground. So finally, so from this, you can see this cross. This is crossing actually. These beams are, electron rays are crossing here. So this is basically, the dimension is called D0. D0 is basically a source, source spot size actually. After that, beams start converging actually from here. So first they are cut at the anode plate. So unnecessary electron beam are cut here. So you can, so when you apply voltage here, you change this voltage, you can basically select how much you want to disperse. So everywhere you are provided a very nice control. You can keep on controlling. So now from so this point, so this point is this point becomes this point. You can see this, right? This and this. There are two ways, two examples how beam can be made to converge at a small probe in your sample, right? For example, this is your sample, and you want to converge. For example, you do this SEM, scanning transmission electron microscopy. There you need to converge the beam onto a small spot. So this is the example how it is actually done in the illumination zone. So this point is your gun crossover. This one, it becomes this. So now you put this condenser lens 1. So this gun crossover becomes the object plane of C1, right? So this is object plane. So the rays are taken from here, and then after that they are converged here. Okay, you can see similarly. So you can see that here the current is smaller. This is all of these are magnetic lenses. So if you see that here the focal length is larger. So if the focal length is larger and this angle becomes smaller, so this angle is larger, this angle is smaller, and this focal length is larger. So what do? You decrease the current of this lens. So when you decrease the current of this lens, so this focal length starts shifting away, right? If you make this lens stronger, so this you have to just press the you have to just turn the knob, and you can increase or decrease, like your regulator in your ceiling fan regulator, exactly the same way, nothing much different, right? So you can make this, you can change C1 setting, and it's a strong C1 crossover, right? So there is some noise. Can you mute yourself, please? Yeah. So after that, there is C2 lens. C2 lens also works as a as a diaphragm. So you can see that this is next condenser lens. So after that beam, you can see that if you take this this is a focal point. So if it is here, so you can see that divergence will happen, and this shaded area, the electrons are cut by this diaphragm. So these electrons are not reaching to this point, and which is actually important, because if all these electrons are allowed to reach here, so this because you're converging a lot of current, because current density will be very high, so you can burn the hole in your sample. So that it's better that you select only part of the electrons, and rest of the electrons are blocked by this diaphragm. Got it? And here, if you make this lens weaker, so you can see that you can start making the beam parallel. Okay, this is, you can see that this is tending to become uh, parallel beam, and here you are converging the beam. So we'll see a lot of these kind of examples. Uh, TM operation using parallel beam. Condenser does not always condense. You can see that condenser, we can see condense. So this lens C1 always condenses, but C2 doesn't always condense. You can condense it and you can diverge also, right? Though it is called condenser lens, right? So somebody's mic. If you have any questions, Shiva, your mic is open. So you have any question? Shiva, do you have any question? Okay, so let me move to the next slide. So C1's, you could see that C1 and C2 lenses are adjusted to illuminate the specimen with a parallel beam of electrons. So in normal TM imaging, the beam is mostly parallel, right? And you basically shine several micron area. For example, 20,000 x or 100,000 x. So typically several micron area of your sample is getting illuminated. So this is all we have learned, right? So another example is that how you make perfectly. We saw that how to make focused beam, convergent beam. Now in this slide, you will learn how to make a parallel beam. So same thing, we can start from the gun crossover, and this is our C1 lens. So you can see that this is the image, this is the object plane, this is the image plane. So here we form the image of the crossover, right? Uh, any question somebody is having? Darren, do you have any question? Darren, do you have any question? Yeah. Uh, so you can see that the C2 lens, if you under focus C2 lens, you can see that under focus basically means this angle will become much smaller. You can see that this is a specimen. So if you weaken this lens, then you are making this. This is one of the way to make parallel beam, almost parallel beam. And another way to make parallel beam is basically these old-fashioned TMs had only C2. They didn't have this upper objective lens. Now most of the lenses have, you can see that it's written there, no TM has only two condenser lenses. There is third one, which we call upper objective lens. Or you can call it condenser, and there is a basically twin lens. It is called twin lens. So one part of the lens is here above the sample, and another part of the lens is below the sample. So this is the most important sample. I will tell you, many students, I'm getting a lot of queries from time to time, that how to image the magnetic sample, right? So you can see that magnetic sample, suppose your sample is in magnetic nature. So what will happen that this upper objective lens, it is too close to, it is basically kept only few millimeter away from the sample. It looks very far here, but it's not very far in principle. So sample is basically like tucked in this upper objective and lower objective lens. So you have to switch it off. You completely switch it off and don't use it. You don't need to use it, because you can see that you can just use C2 lens to serve the same purpose. So so if you switch it off, then this lens is quite far, and so particles are less likely to be. The magnetic field from this lens will be very weak on your magnetic samples. So it's not very likely that the particles, magnetic nanoparticles or something, will fly towards this. It is quite likely that your upper objective lens can get damaged if it is turned on. So I hope you got the solution. Yesterday also somebody asked me. I was in a meeting with the industry last evening, and that scientist asked me that how to take care of the magnetic samples. So now now you know that you can just use C1 and C2 and turn off the upper objective lens, right? If you do not turn it off, then this lens in fact helps you to make very nice parallel beam, even quite nice actually. You can see that, right? Any question here? So let us move to the next topic. I think you remember this slide. So there is no specific purpose of keeping this slide, but because this sometimes students get confused that what do you mean by under focused, over focused. So just to refresh the memories, I put this schematic which we have already investigated in previous lectures. So over focus means this lens is stronger and this angle is more, and you're focusing here. This is perfectly focused. This is under focus. As I said that this is yeah, this is already covered. So you can what to do for a magnetic sample. So you can turn it off. This makes life more complicated. Upper objective lens. Got it? So you can just request the operator. Sometimes some operators may not be very happy to do that, do this favor to you. But if somebody turns you down, that your sample is magnetic in nature, I didn't want to do that. So you can tell them that what to do. And another way is that you should make sure that your particles are not flying around, magnetic nanoparticle. Most of the time, let me tell you from my personal experiences, these magnetic nanoparticles are not that magnetic to fly off, and their magnetism is quite weak when they are in the nano size. Most of the time, they are super paramagnetic, right? They are not like permanent magnets or hard magnets. Hardly they are hard magnets actually. So this worry is not very minutes. So if you have hard magnetic samples, which very strong magnetic field, so they can. There is another problem that they can disturb the magnetic field from the sample itself can also disturb the electron rays. But fine, anyway, it is better to avoid the problem. So this is how you can do that. So this is the repetition that this upper objective lens is sometimes called as C3 lens, right? The basic principle is basic principle using just a C1 lens and basically under focus C2 lens. So you under focus C2 lens is the basic thing, unless you want to use the other one, right? So you can read all these things. So now we are done with the lenses in the illumination zone. You remember that we are just learning the illumination zone, the settings uh, in the system above the specimen. Now what we do with the diaphragms or aperture. So you can see that again you start from the gun crossover, then you have the C1 lens, and then you get the image of. You always start from this point, and then it becomes very easy. Now you have a C1 crossover, and this lens to me it looks very strong because the focal length is very strong. So if you have this strong focal length, so you can see that here at C2 lens, condenser 2 lens, and condenser aperture, most of the electrons you're cutting. You can see that only the solid, under the solid lines, electrons are able to go through. The other sides, electrons are not allowed, they are blocked with this uh, metal plate or, okay, metal plate, usually metal plate. And if you weaken this lens, so what will happen, this angle will decrease and the electron density will increase. So basically you are also, diaphragm is not just, diaphragm plays a major role. So in fact, you can use diaphragm also to make parallel beam. So what you learn here is that not necessarily only the lenses, diaphragm also play a major role in giving you, controlling the beam type, whether parallel or convergent. You can see that here. So next one, convergent beam. Sometimes we want to focus the beam more so that intensity of the beam on a specific area of the specimen is increased. How can we do that? If you want to minimize the area of specimen that you are illuminating. So same thing, what we will review the same thing, that it is done by C2 lens, right? When you, I have, this morning I wrote these lines to revise this thing. So when you convert the beam, then you would like to cut the current, okay? When you make a parallel beam, then it is not a good idea to lose electrons, right? When you are making parallel beam, so this, because per unit area, electrons passing through your samples will be less, so it is not a good idea to reduce the electron density. So you would not like to use aperture to cut the number of electrons. But if you are converging, so it is better to cut. Even this, you can see this shaded area shows you the shows you that a lot of electron flux is stopped by this metal diaphragm, and only few of them are able to reach to the sample. So these are the settings, right? Now let us move ahead. You can review this thing later on. So next point is that once you have this convergent beam, we call it nano probe also these days, nano electron beam. So it is easy to get the information from this tiny spot. But you want to raster scan, you want to move this spotlight all across the sample to get the information. So how do you do that? You cannot move this source, right? The source is fixed. So how can you move this spot? So this is called traversing the beam and tilting the beam. So these are two scan coils, upper and lower scan coils. You can see the couplets. These are the scan coils. So you can see two examples that this is the real source. Source is not moving anywhere, but when you change this settings, so when you basically change the settings of the upper and lower scan coils, you can see the beam tilts actually at this uh, plane. The beam is tilting like this, and then at this plane, the beam is tilting again. So earlier you were, for example, earlier you were illuminating this area. Now you are illuminating this area just by applying magnetic field to these lenses. You're able to. So this appears that this source has moved from this to this. You can see this dotted line, right? But the source has not moved. So it just, you have tilted two times, right, from here and here. So uh, similarly, you can see it here, so that you can. So this is how in scanning electron microscopy also SEM. Same thing is done in SEM, right? We have learned about SEM. There, I didn't tell you this tilting because it's already covered here. STEM and SEM, this is how the beam is raster scanned, right? Without having to move the source itself. So the virtual image is formed, basically, something like that. So let us go much deeper. Yes. So many of you will be excited to see uh, this thing again, because some students have doubts even now. So it's a revision for many of you. Many of you are joining newly, so it will be good for either in either case. So so if you see that the TM images are formed in two stages, right? So again, we start from the electron source. This is condenser lens C1. This is C2, and this is the specimen. For example, this arrow is your specimen. So now, once these electrons pass through this, so okay, we are talking about now the image plane, okay, not the illumination zone, the second one, okay. Now a lot of fun starts here. We are not considering this part above the sample. Let us see. So this is your specimen, the arrow here. And once the electrons have passed through this specimen, carrying the information about your specimen, then this is basically stage one. So this is back focal plane, right? And here you put this is basically objective aperture, and this is selective area aperture. So you can see that here this is inverted, right? In this arrow is inverted here, and again you have this second inversion. So each lens is basically doing this inversion. Finally, in the image plane, you see the same uh, beam, magnified beam, magnified image, as you can see here, the magnified version of your specimen here. What it so what exactly happens that yeah. So in this process of forming the primary image, the objective lens, this is the objective plane. This is your spin. This is the lens. Objective plane, objective lens basically produces a diffraction pattern. At we all know that it produces diffraction pattern at the back focal plane, and diffraction pattern is nothing but the Fourier transform of the scattered wave. So we have learned that all the diffraction patterns are Fourier transform. They are inverted from reals to reciprocal space. Fourier transform means why do we need Fourier transform? We are transforming from real space to basically K space, right? Inverted space or reciprocal space, one over D or K, right? So if you want to have diffraction pattern, so you do the Fourier transform one time, or if you do it another time, then you finally you do another Fourier transform of the diffraction pattern. So finally, you can make basically your images in HRTM, which is called phase contrast microscopy. This is two-step process. So first you form diffraction pattern, and then another lens basically uh, uh, does second Fourier transform, and then you have the HRTM image, right? So high resolution image, as I have always reminded that it is an interference pattern of direct beam and diffracted beam in your back focal plane, right? So you can understand what is going on from this schematic, that this is your electron beam, parallel electron beam, and these are your lattice planes. This is your inter plane distances, right? And the beam is almost parallel. Beam has to be almost parallel to the lattice plane. You can see that unlike in electron diffraction, unlike in X-ray diffraction, where the X-rays fall at a quite large angle to theta, here beam has to be quite parallel. What is the reason? So the reason is hidden in the Bragg's equation. 2D is equal to n lambda sin n lambda is equal to 2D sin theta. So here D is the same. Your D is your lattice spacing, right? Interplanar spacing. But what has changed is lambda. So lambda has become almost 100 times smaller. So if the lambda has become 100 times smaller, so angle also approximately becomes 100 times smaller. So 10 degree to theta in X-ray diffraction corresponds to roughly a few like 0.1, 0.2 degree. So that means this has to be almost parallel. So only then these planes will diffract. So when these planes diffract, so they will form like 0, 0 HKL, basically 0, 0, 0 undifracted beam, and then you have diffracted beam from HKL planes. So all the family of HKL planes. So right, family of planes HKL. Like there is one set of plane and then a family of planes. If you look from different directions, they will all diffract, and it will form basically a cone, diffraction cone. Diffraction is always a cone. We show it by this arrow, but if you rotate this arrow along the optic axis, so this becomes like a cone, like birthday cap. So it's always like that, right? So if you take another family of planes, then for example, if they are diffracting at higher angle, so then there will be another concentric cone. So there are several cones actually. Okay, so this is misleading. These arrows, just in your mind, uh, rotate these arrows like the like this. Just if you have this two fingers at an angle and you rotate like this, you form basically cone, right? So that is exactly the problem we will see. Why do we need a better system to look at those diffracted electrons? Yes. So now, so diffracted beam, you can see that this is 0 or O, you can call it O. This is basically, these are undifracted beams. So, right, this is your sample. These are crystalline plane of your sample. Spacing is D, and this is lambda, wavelength of electron beam. This is your illumination zone, and this is your imaging zone. So you can see that the undifracted beam or 0, 0 diffracted beam focuses here, right? This will become the central bright spot in your electron diffraction, and all those beams which diffract at angle 2 theta b, right? They will form this one basically g, right here, and minus g and minus g, and then other higher orders will form like 2g and minus 2g here, 3g and minus 3g. So this g distance, this so g vector is basically the distance. Somebody was asking what is g. G is always 1 by d, right? 1 by d. D is basically the interplanar distance. So, so you can see that if when you increase, so this is your g from distance from 0 to g is your g vector. So larger this distance, smaller your d, right? So for a smaller plane, if you take another plane in between, imagine another plane, so your d becomes half. Now what will happen? Those planes will show the diffraction at 2g, right? Which is basically larger distance here. Though this distance corresponds to smaller d, smaller interplanar distance. You can see what we are doing. We are doing the reversal. We are going from real space to imaginary space. So we are basically taking the Fourier transform. I hope you can understand. Naturally, Fourier transform is happening. Any reduction in here is increasing the distance. Please note that, because G is 1 over D. So this is essentially like Fourier transform, right? If you reverse it, if you put another lens here and if you reverse it, form image out of that, the way we do in bright field, dark field, then basically you're going again into the real space. This is, if you stop here and you make, if you just capture this, if you capture it here, then basically you are capturing in the reciprocal space or a Fourier transform of this thing, right? So please note that. So this is your diffraction pattern. Central beam HKL 000, and this is your G spot, right? And this is 2G, and this is 3G, minus G, minus 2G. These are all diffraction spots, right? These are all diffractions. These are this central spot, and then these are all. But please note that this cannot be a linear. This is not a linear thing, right? This is three-dimensional. So I'm again. So if you take this diffraction spot and you turn it around uh, optical axis, then it becomes a ring. This diffraction spot becomes a ring actually. So all these will become ring. This will become another ring. This will become another ring, right? So if this is a these are crystallites, polycrystallites. If it is a polycrystalline sample, so there will be a lot of this diffraction happening from these crystallites, and then uh, you can have ring kind of a pattern. You will have concentric rings actually around the optic axis. So uh, if you have any question, you can ask. So entire thing can be understood that this is your specimen in the real space f function of x and y basically real space. So after you pass these electrons through the objective lens, right? Then you are what you are doing is you are basically Fourier transforming it. So UV is, you can say that it is in the reciprocal plane. F, this large capital F is the Fourier transform of this function. Okay, you're going from real space to uh, K space, and after that you magnify and again you are putting another lens, right? Another lens. Finally, you keep on Fourier transforming. So you can see f function here and another f. So you basically come back to the real space, right? This two times Fourier transform. On real space, one time you go to the reciprocal space, and reciprocal space Fourier transform back to the real space. But now you can see the new value is m times x comma m times y. So that means this specimen is magnified m times in the image plane now. So you have a choice if you want to do one time Fourier transform, then you will have the diffraction pattern. If you want to do it two times, then you have the HRTM image or whatever your selection is. Now, camera length is already covered. So this is another shot of repetition, and you can see the L is equal to R divided by 2 theta, right? It is usually sine theta, but sine theta is, the theta is very small, sine theta becomes theta. Uh, now, so you can see that this image is of certain neodymium calcium oxide. It's taken from this reference. So the voltage is 200 kilo electron volt, and camera length is 0.5 meter. And this is the diffraction mode. You can see that from this area. So this is to demonstrate that once Fourier transform will give you diffraction spots basically. So this is okay. You can assign one of the bright spots as 000, and then neighboring you can start calculating. So you can start indexing which one of these points is what by calculating the distance here. Right? You can calculate the d values and take some help from your extra diffraction. And if you do the Fourier transform of this, you can get the HRTM. So many times what students they do, they capture, this is high resolution transmission electron microscopy image. So you can see that this is done. This is taken from the interference of direct beam and interference beam. When you have direct beam and diffracted beam interfering, then you have this. This is basically interference pattern, right? Twice a Fourier transform. So what students they do, they just they have not taken the uh, selected area electron diffraction, so they will just do the one more Fourier transform, they will get this, or they will do the Fourier transform of this, then you can get something like this, right? And you can mask also certain spots. So another point, another way is that basically, suppose there is a lot of noise here in the HRT, and a lot of planes are intersecting with each other and a lot of fuzzy. So you can do Fourier transform from real space to imaginary space, and you select the diffraction spots which you want actually, right? And mask other points. Okay, remove other points because they might be coming from the plane which are making the which is making the analysis much more difficult. So one by one you can unmask one point, and then you do the reverse Fourier transform. So you can see, suppose you want to calculate that interplanar distance here, and it is very confusing HRT many times. So in that case, to remove the noise, so if you don't see, you're not able to see the planes clearly. So this really helps. Okay, so take the Fourier transform of this, mask certain points which are not of your interest, and unmask only those points which are of your interest, and then do the reverse Fourier transform. Then you get much cleaner image, and calculate the d values for that series of planes. Now you can do this for another spot, right? For example, you have selected another spot which you had masked earlier in first round. So then you unmask the that point, and then you do this, keep on doing. So you can basically look at the different the values, right? Um, it becomes very useful, actually, useful tool. Any question so far? Any question?
Sir, Harshit here.
Yes.
Sir, sometimes we get the Moire fringes at high resolution. So how to
Moire fringes? I'm teaching in Fresnel fringes. There will be separate. Don't worry. You are now attending my lectures, so every question will be nicely discussed. Moire fringes. So okay, I can just cover separate. Just give you a flavor. Moire fringes. How do you differentiate the lattice fringes from Moire fringes?
Yes, sir.
So Moire fringes normally basically happens. Basically, the d value is much larger. D value is not the lattice fringes. Okay, and Moire fringes basically happens when you have one lattice plane sitting on top of another lattice. Actually, so there's basically intersection, right? So when there is an overlap, for example, you have one nanocrystallite sitting over another nanocrystallite, nanoplate or whatever, nanocrystalline plate. So then you can, so Moire fringes will happen that when electron beam passes through one of them, and then same beam passes through the second grain. So then you get this, and then when they cross each other, then you get this interesting pattern. And I'll show you many examples from real life of Moire fringes. And as Harshit has taken this example, there is a reason why Harshit has taken this example when I was discussing Fourier transform masking. Probably he has done it. So if you have Moire fringes, so this technique, what I just discussed, same technique can be used to clean up Moire fringes. So you can do the Fourier transform. Fourier transform is so excellent, an excellent tool actually. So you can remove one, you can mask one plane and do the reverse Fourier transform, and then your Moire fringes you can clean up actually. One of the ways is like that. Okay, Harshit, I'll tell
Okay,
you
sir.
it will. But I'm happy that you asked this question. At the right time, you asked this question actually. It's the right time actually.
Okay, thank you, sir.
Any other question? Samina Mulani? Samina, any question?
Sir, I have one question.
Who is the person? Dubai, yes, please.
Sir, sir, in 10, when we do,
Dubai,
we
did you
got the
eat your
SAE.
breakfast today?
Yes, sir.
Okay. Yes.
Sir, when we do normal 10, we got SAED pattern. But when we do H at 10, we got FFT pattern. Then what is the difference between SAED and H?
Repeat the question.
And when we do normal 10, we got the SAED pattern.
Yes.
But when we do H at 10, we got the FFT pattern. What is the difference between SAED and FFT?
No. See, HRTM image is the Fourier transform of your SAD pattern, including direct beam, including the center spot. Okay, so HRTM image is forming in real space, and the diffractions pattern is always formed in reciprocal space. So basically, you are taking Fourier transform of diffraction spots, which is called SAD. When you take the Fourier transform of SAD, then you get HRTM, and that is essentially the difference between HRTM, bright field, and dark field. Bright field, you take only one beam, direct beam. You do not take multiple beams from your diffraction pattern. Please note that here, suppose I take only one beam, which is direct beam, and I do the Fourier transform of only one beam. Then what I get is bright field image. I will not get these kind of fringes because I'm taking only one beam. So these fringes happens when I'm taking more than one beam. So more than one beam, basically they interpret with each other. These concepts will be clear today itself. Don't worry. Just wait. Yeah, you have it here.
Hello, sir.
Yes.
Hello, sir. This is Amina.
Yes, Amina. I'm happy to hear your voice.
Yes, sir. I have one question. That how?
Amina, you are from which?
Yes, sir.
You are from which place?
Actually, sir, I am from Pune, but now I am doing PhD in IIT Indore.
Okay. You are from Pune University, huh?
Yes, sir. Yes, sir. Pune University.
Amina, bolo.
Yes, sir. So I have one question that how actually Fourier transform is done in TM, means how it is performed, whether it is a special software or something.
No. Okay. Okay. So there are two ways. One is basically through software. Another is through hardware. So when you use this lens system, so it's way of teaching that lens system itself is doing Fourier transform. So for example, when the electrons pass through your sample, so they carry the information about your sample, and when you form the diffraction pattern, so that is basically your. It's a way of telling that you are doing the Fourier transform. Fourier transform came. The mathematics came later. So because
yes, sir.
Right, this was the mathematical way of. So scientists were very clever. They realized that they did some calculation. They realized, oh, it looks like Fourier transform. So why can't we do it using software? So now you can use the software, right, to do the same thing, which lenses are doing. Got it?
Yes, sir.
So you
Yes,
can
sir. Yes, sir.
offline also. Yeah.
So, sir, that means that Fourier transform is transform us in from real space to reciprocal space.
Exactly.
So that's what that interplanar distance get reversed.
Get reversed, exactly.
Yes, sir. Yes, sir. Okay, sir.
Yeah. So suppose you forgot to take a diffraction pattern, so you can take the Fourier transform, and you have HRT image. So you take the offline. You can do the Fourier transform of HRT image. You will get the diffraction pattern.
But sir, how we will going to take that yet Fourier transform of image?
It is by software. It's by software. Software does
okay,
it.
Okay. Okay, sir.
See, if I were a PhD student in my when I was a PhD student of physics back in 1995, so so this was exactly my project. Actually, this was a project, first project which I got in my computational physics class. Immediately, it was probably October 1995. I joined in July 1995 in PhD program, and then I joined like this pre-PhD coursework. So within 1 or 2 days, the professor who was teaching, immediately gave me this coursework that you do the Fourier transform, and we were a team of 2 people. I don't want to name the other person. He's a very good friend of mine, so it is not good to name. But that was challenging for us that time. You can understand now, but
Yeah.
so our life was much more challenging than. So we had to learn essentially what is Fourier transform, and you have to make computer program that you have some signal and you have to Fourier transform it. Now it is done easily by click of the button, but we had to make program. We didn't have softwares at that time. So every software we had to make it actually. We had to write the code.
Yeah. Yes, sir. Okay, sir. Thank you, sir.
Any other question?
No, sir. Thank you.
Then you can mute yourself.
Yes,
I
sir.
can see from other, there are many students from University Physics Department. Lohar, I think, I forgot your first name, Amrita Lohar. Yes. Any question?
No, sir, not right now.
So what is your first name?
Same, I have written my
Amrita,
original
you have
name.
written it properly. Yes, yes.
Yes, sir.
We have met quite a few times. Are you enjoying the lectures or it's getting a bit too much?
No, sir, I am enjoying. It's just
Okay.
good. I mean,
Okay, okay.
they're good
So
topics.
any other question? Darren, you have any question? Himanshu, please ask. Rijwana is silent. Rijwana is preparing for probably her PhD viva. Rijwana, how are you doing?
Good, sir.
Huh?
Yes, sir. Good, sir. I'm fine, sir. Good.
I was not expecting you. I thought you will be working on your slides. Anyway, good to see you here. Yeah. Yeah. So yeah. So why should we need? Why do we need to select the area? Okay, that question is there in this slide. Why do we need? We always call selected area electron diffraction pattern. So diffraction. I mean, one answer is very obvious that see diffraction pattern from a larger area is not a good idea because the real life samples are quite thin film and they will see this problem is also solution that buckling actually suppose I show you for example paper. This is a paper and this is your actual sample. So this is not exactly, even in atomic force microscopy this is a problem. So no, there is no flat area when you take larger length scales. So if you, because the sample, real life samples are all buckled, data meda, right? So it is always good to select a smaller area which might be straight. Now you can ask this question that no, I want to take electron diffraction from a buckled sample. For example, sample is not straight like this paper and it is tilted. I will show you, I will stop sharing and then show you on the larger screen. Now you can see me holding the paper. So normally, suppose this is your paper and this is, even atomic force microscopy, the same problem. When I will teach AFM, I'll tell you how to make this to this. Usually samples are like this, or they can be like this, they can be like this, got it? Or they are curved like this, or they can be like this also, like wavy, like this, got it? They can be like wave, okay, but they can real life samples, right? So they're not necessary. So it's better. So now the question comes: if the sample is like this or like this, so when the electron beam is passing through entire sample, so what will be the changes? What do we expect the changes in electron diffraction and um, real images? So there is basically, I'll show you examples from my own lab. And few slides in future lectures is reserved to understand this, and this becomes very useful. You start getting these fringes. Actually, you get fringes, very very nice fringes you get, and a lot of work in electron microscopy. Country's best work is done at BHU, where uh, Harshit Agrawal works in the metallurgical engineering. India's historical work in electron microscopy is done there. Okay. Yeah, I hope
Yes.
you're aware of that, right? So one of the best place to learn. Okay. Anyway, coming back to the so number one, that samples are often buckled. They are not the way we want them to be. So, for example, you say that electron beam is entering at certain angle to theta um, with respect to the lattice plane, right? But if it is sample is buckled, so that means your lattice planes are also buckled by certain. They are changing actually as you go from one spot to another spot. So if they are changing, then how would you imagine the diffraction happening? So that is very interesting actually. So right now we will say that okay, we are looking at some selected area. Second point is that direct beam is often so intense that it will damage the viewing screen or saturated CCD camera. That's another reason you can select. So now next question is that how small area can be selected in selected area electron diffraction? How small area? Uh, so basically, yeah, that is fine. Okay, now I thought there is another point, but okay, I'll teach this one first. So there are two ways you can reduce the illumination area. One is by taking convergent beam. So this C stands for convergent, B for beam, E for electron, D for diffraction. Convergent beam electron diffraction is highly useful thing. It gives you a lot of information. The second one, we normally somehow in India, very few people use this, but it is getting more popular in India. CVED, you will hardly see any paper from India doing CVED. If somebody is interested, I can teach this, but I will not be teaching this because it's a specialized this thing. But if somebody is interested, so it is off the syllabus. I can teach a separate course. Anybody, any question? Darren? Yeah, and you can mute yourself. Yeah. So second point, which is more popular, is basically you insert the aperture above the specimen and then allow illumination only from the selected area, right? CBED is, what you do that this is your thin specimen and you take the convergent beam. So this is your angle to alpha and the beam becomes a disk. So I told you that, sorry, the spot becomes a disk. So earlier this was 0, 0, 0 diffraction spot, the central bright spot. So this was a point actually, point. Okay, so now you can see that because beam is converging, so this has become a disk. Now this distance is A, right? And now this HKL spot earlier was a very tiny spot. You saw the diffraction pattern. Now it is a disk, and there are a lot of features inside. There are a lot of lines, Lovey zones you can see, which you can analyze and get a lot of interesting information. So again, it is three-dimensional. You will see all around that. So this is misleading. So because this entire thing is conical, so you will see a lot of these points. Uske piche, from in front, you see all kinds of these patterns. Way to put the selected aperture. So basically, Nilu Bhai, the student from Saurashtra, he had this question. I remember that he wanted me to teach again and again these things. So I thought, so you basically put the aperture. So to make diffraction pattern with the parallel beam of electron, we have to use the selected area aperture. We can't insert aperture obviously in the specimen plane because there is a specimen already there. So we insert the aperture in the plane which is conjugate to the specimen. Which plane is conjugate basically? Let's see. So so you can see that this is basically your back. Okay, where these beams converge basically. So you can see that this is your specimen, and so these electrons are coming from here, and so So this is your lower objective lens. Okay, upper objective lens is just above this specimen, and after passing through the sample, some beams will go straight and some beams will diffract. So so this is back focal plane, and this is your image plane, and then you can put the aperture here. So this is basically conjugate to this plane. You can see these two. When you put this aperture here, it basically it's a conjugate plane actually of this. So okay, this is not a very clear image, so I magnified this. So now you can understand the entire thing, how the diffraction. So let us start from the specimen. We are not discussing the illumination zone. We are just looking at the other part, lower part, right? So you have this lower objective lens, and yes, this is your selected area electron. So suppose you want to make. So there are two cases here. I'm sorry, I'll just move this. Yeah. Now look at this very carefully. So there are two examples. In one example, we are tasked to make diffraction pattern DP, and here we are making HRTM. This is HRTM mode, and this is simply diffraction pattern. So if you see that in when we want to make diffraction pattern, so first thing is that you have to remove the objective aperture. You can see that this is removed, number one. So we don't need it here. When we make the image, HRT image, then we need to put the objective aperture back in the back focal plane. BFP is basically back focal plane, where these beams focus. You can see these beams are merging here. Okay, so this is basically back focal plane. All these beams are merging here, the back focal plane. You remove this first, and then you insert the SAD aperture. Okay, here we have removed SAD aperture and we have inserted objective aperture, right? One of these. So when you're taking DP, put this aperture, remove this, and opposites to here. And the planes are different, you can see that. Now, this aperture will decide the area, okay, size of the aperture. Now, but this is allowing, you can see this is allowing all the beams, diffracted as well as direct beam, to go through the following lenses. This is another lenses, intermediate lens. So you can change the strength, and then you can change the focal length. And this is fixed strength because it's a projector lens. So now using these lenses, you can focus diffracted beam from different planes at different spots. So you get this 0, 0, 0, HDL 0, 0, 0 spots in the center. And then you get all kinds of spots, beam which are diffracting from different planes, focusing on these different spots, right? So as I mentioned that G minus G, 2G, 3G. Okay. If you don't want a diffraction pattern, so you can remove this and you put this objective aperture back. And then if you notice that again this aperture is allowing, we'll see another case, it's allowing both diffracted and undiffracted beams. So this is basically HRTM, high resolution TM. This is not bright field or dark field. In bright field, we select either diffracted or undiffracted beam. Please note that this is HRTM mode because we are allowing both the images, both the beams, and they're interfering here and forming the image here. Okay, so yes, so this is a bit magnified, so you can see. This question is often asked by students that how small area I can select. So I mentioned when I was teaching apertures that you cannot make aperture smaller than 10 micron because of the machining issues. And so if you take demagnification by 25, so the minimum selected area is around 400 nanometers. So thumb rule basically just, if you can remember that half a micron area you select usually. So if there are other innovations, I'm not aware of that, but this is what information which I have. Now, if you select one of these beams, either diffracted or direct beam, then you get in the image plane. Let me remove this animation. So here you can select between bright field and dark field. So yes, so what is the difference between bright field and dark field? Uh, this is very simple actually. So let us understand first the bright field. Again, we start from specimen, and these are parallel beams. These are parallel beams, and these are your lattice planes, which are reflecting or diffracting, whatever you call it. Usually the term is uh, diffraction, but you can use them as a mirror planes to understand things better. So, so beams will diffract at certain angle to theta. Now, again, this schematic is misleading because uh, these planes are not just diffracting here, but they are diffracting conically. So there will be cone, right? You understand? There will be cone around that. So like here and here, all around angle theta, 2 theta. But if you notice that if you put this objective aperture, we saw that this objective aperture, this one, sorry, this one is objective aperture, this one, right? So this is used, this is very helpful. Now, entire game is of this, how do you place. So if you put this objective aperture in such a way that you are blocking this as well as this, see this diffracted beam will be focusing somewhere here also back there, but it is a disc, metal disc, so it will be blocking all other diffracted beams and allowing only the beams which are going through this uh, aperture in this diaphragm. So if you look at the pattern on the image plane, so this is the direct beam. This is the direct beam here, dark one, bright one, but it's shown as this one. And okay, so this is the optic axis. Okay, so this will be formed here, and these all of them you are blocking. If you make the image out of these electrons, so then you call it bright field image. Okay, if you use these electrons to form the image, then you call it bright field. So if you magnify these electrons, you cannot get HRTM. Please note that in HRTM you allow this as well as this both. But you have to allow both of them in HRTM. I repeat that if you allow one of them, so undiffracted, you get bright field. You allow any of the diffracted beam, so you get dark field. So what is the obvious use of dark field? Dark field, you can see that this beam will form only when there is a diffraction happening. That means these areas will light up only when there is a particular family of planes present. If the family of planes is not present, so essentially you are investigating whether your sample is crystalline or not. So this beam will anyway go even if your sample is amorphous, even if these planes do not exist, you will get direct beam. So this doesn't tell you a pure crystallinity information. Yes, if there is a crystallinity information, it will be there, right? I told you three informations are hidden: crystallinity, mass, and thickness contrast. But now you can separate this. You can light up only those areas where these planes are present. For example, I have selected 111 planes. So this is 111 plane. Now what I've done, look at this here. So this is bright field, dark field is here. So now the direct beam I have blocked. Entire direct beam is blocked now. I'm not using this for imaging. I'm allowing only once this my aperture is placed here, so I'm allowing only the rays which are diffracted from whatever I want, the plane which I want actually. For example, 100, 111, 211. So those planes are diffracting. So when I make the image out of that, other areas will look dark and only this will shine up. Those platelets or those areas will light up which are aligned in that particular direction. So I can select now, but the problem is that diffraction doesn't happen like this. Diffraction happens in a cone. So these planes are not just diffracting here. The same planes will be diffracting all over theta. You know, it's like a ring. It should be like a but I'm selecting a very small intensity because I cannot make. So I should be if I want to catch all those diffracted electrons at angle to theta. In principle, this uh, aperture should be concentric annular ring. Actually, there should be a it should be like this. Concentric ring should be there, like this, right? Like this. Suppose this is solid. Inside this is solid. This is and this is empty. Reverse. So and this is angle theta, 2 theta. Sorry. So, but real life you cannot make aperture like this. Can you make aperture like this? No, it's not possible. You cannot machine it. It will fall off. Oh, sorry. So what do you do to? I'll tell you the hollow cone method, and it's another topic. Um, but there is one way out to this problem. What do you do? That another problem in this mode. I think Dubai or somebody was asking that why don't you do the dark field imaging by using these kind of beams, right, which are diffracting. This is the natural way of doing things because diffracted beams, they are diffracting at a certain angle. But if you notice, there is one problem that this is the objective lens and this is the center of the objective lens. Now, we know that lenses are not perfect. The magnetic field is weaker here in the center and it is stronger here. Now, what you are doing is that in one mode, you are using the central part of the lens, which is the magnetic field is uh, mm, uh, different, and then magnetic field is different here. So that's not a very good choice. So we should be using the same area of the lens so that your magnetic field remains the same. This is one of the strong reasons that rather than you allow the beams to pass through the edges of the lens, which you are doing here, right? Your beams are shifted towards this side. This is not a very good choice because of aberration. So what you do, you tilt the incident beam. We have seen how the beams are tilted. There is a tilt. There are tilt coils, so you can tilt the beam, and so now you can see that direct beams are. So these are basically direct beam. You can see these are direct beam. They're tilted. Now they appears as tilted, but they are not diffracted. Now you are blocking your aperture position is the same, lens is the same, so now your diffracted beam will be straight beam. You can see that. It's very clever design, right? So you avoid this problem of aberration just by tilting the beam. Any question here? Is it clear? Just open one of these.
Yes, sir.
Yeah. I think there was, okay. Nilu, is it clear now to you?
Yes, sir. Yes, sir.
Very good. So
Thank you.
Yeah. So you will get these slides also.
Yeah.
This is still Nilu maybe may not be very. Yes. Sorry.
Nothing, sir.
Okay. Yeah. Okay. So Nilu may not be very happy. Nilu may demand more and more. Students like Nilu may not be still happy. So they may say that yes, I'm taking as I told them that so we have This is called center dark field operation. So this is basically called center dark field. Okay, so this is called CDF, center dark field. And this is called aperture shifted dark field. This is not a very favorable thing. You are shifting the aperture. Aperture shifted, whatever name, I don't remember the name. But this is the problem. You can see that off-axis electrons are greater the aberrations, and stigmatism will also be there. Displaced aperture, shifted aperture, or displaced aperture. So this is the right way of doing things. Center dark field is the right way of doing things. So to answer the students like Neelu, there is another technique which is called hollow cone diffraction that I will teach on Wednesday. I'll see tomorrow if I'm free. I'll announce it tomorrow. I may take a class to finish it off fast. Yeah, because one day Rijwana is going to take, but that is Tuesday actually. Yeah, so Tuesday I have to give another lecture. JNU has invited me for some lecture, so I have to find, because that the timing is also, I have to drop one lecture next week. So we'll see. So yeah, so I'll just pose this question in your mind. I will plant this problem in your mind, so you keep on thinking. Now the problem is that the diffraction is happening like a birthday cat, right? This is your angle of diffraction. So diffraction is happening all over. Now what you are doing is you are putting the aperture like this. Got it? So when you put the aperture, you are basically selecting only one specific beam. You are cutting other spots. That's not a very good idea. So what you do, basically you spin the beam. So one way is basically you make the aperture like this. Got it? This white, but can you make aperture like this? This central area will fall off. You cannot make, you have to connect these two, outer and inner. Na? These are two rings actually. Outer ring and an inner disc. This is outer ring and inner disc. So you have to take this, you have to make a cut here. So you can't do that because this will just fall off, this will separate. So what you do, you basically spin the beam. I'll just show you. Basically, this is called hollow cone. So basically you spin the beam in a cone rather than, I showed you tilting. Either you can tilt at one angle, tilting has a problem. Tilting only you get one specific area. But if you keep on rotating this beam, then it appears that you are scanning all those electrons. Actually, you start spinning this rather than tilting. You basically rotate it. Basically, it appears that you can see that you are just. I'll just show you. So basically, if you rotate this aperture, it becomes a annular aperture, right? So rather than you just rotate it, so it becomes like that. So it becomes like this. It's a very smart idea actually. So and these days it can be done by software. You don't really software does it for you. It's very nice. So for example, this is a bright field image of a nanocrystalline aluminum film, and you do not know which plane is diffracting, which plane is not diffracting, because okay, so this is bright field. Okay, anyway, these are all undiffracted spots. This is hollow cone selected area electron diffraction rather than selected area, conventional one which we normally see. Now this is very interesting actually. You see, this is normal dark field which you do. This is dark field image, right? So out of these so many grains, you see this so many grains. You will, if you want to see which one is 220 aligned grain. So 220, you select that spot and then you make image out of that. You will see that these are the only two grains which are 220 aligned. If you take center dark field image, But if you take hollow cone, you will find that because you're rotating, so you will find that there are many grains here, which are 220, showing the 220 planes, which are shining up from. There are dozens of grains. So this is the advantage of hollow cone diffraction image. So even if you don't have hollow cone, but at least I do not see students using this dark field. Dark field is my favorite actually. I mean, you can select, for example, you want to see which grains are 111 aligned. So just select 111 and form dark field image. You can see out of this khichdi, this is all, lot of grains are randomly oriented. All randomly oriented. You want to see which grain is this aligned. For example, I want to throw this. People are synthesizing all kinds of chalcogenides and stuff like that. I don't know why don't they do it. People are studying. Monica, you are studying this. Monica Galawat, you are studying these chalcogenides and nucleation growth. So this will be a very nice tool for you because you are looking at exactly the same problem. So you can basically light up selected those grains which are growing in particular direction just for example, just first ask the operator to make the basically form electron diffraction dot pattern, and out of that just select one family of spots, make the image. I mean, somebody asked me this question that how do we know which when we are doing this electron diffraction, we do not know which dot belongs to which plane. Fine, no problem. But at least you can do this analysis later on. Just select one or two dots, form image, and then form image. Keep on doing that. Dark field. Yeah. So then when you do the offline analysis, you will know. Oh yes, I selected these dots. Now these are the planes. These are the nanocrystalline, basically what do you call it, grains, which are grown in that particular direction. Even for catalysis people, there are many students from catalysis science. They have this problem because catalytic reactions depends a lot on how you align the grains. And most of the time when you do synthesis in the lab, they are all randomly oriented. And batch to batch, you are wondering that why there is a reproducibility, basically. Yeah, okay. So it's not reproducible. So so this is because of the reason that you didn't control nucleation growth. If you are interested, after finishing all this characterization technique, I can teach nucleation growth. My students will vouch for me that I am a good teacher for nucleation growth as well. And so if you're interested, chemistry student can hang on. There is no exam for that, but it's just optional. So, okay. So this is, you can see the application of learning which you have done today. So much of application is there. If you do not know the basics, you will not be able to understand the potential of these techniques. At least start doing, please start doing bright field, dark field together. Then you explore whether you have a hollow cone diffraction pattern, it is available or not. It's a wealth of information. I can show you tons of examples. Actually, I may have somewhere, but not today. So I stopped sharing today. Just a moment.